So side chain interactions play an important role in the protein structure, and we're going to look more at that here in a little bit. But acidic and basic side chains at physiological pH are fully charged and can participate in ionic bonds within a protein chain and can transfer hydrogen ions from one molecule to another molecule during reactions. So it's important to be aware of their charges. We talked about the pi, or the isoelectric point, previously, and it really influences the protein solubility. So if you have a molecule that's polar, it will be soluble in water, but if it's nonpolar, it won't be. And so this determines which amino acids and the enzyme are able to participate in an enzymatic reaction. So we'll get more into that in the next chapter. So amino acids are all chiral except for one. So chiral just means that a carbon is going to have 4 different groups attached to it. So glycine is actually achiral. It's the only amino acid that's achiral. So just to kind of get a look here at glycine. So we have our alpha carbon, and it has carboxyl group and the hydrogens. We have the amino group. So for glycine, since it has 2 hydrogens, so this right here is our alpha carbon. Since it has 2 hydrogens attached to that alpha carbon, it cannot be a chiral molecule. So that's the only one that doesn't do that. All the other ones have different side chains other than hydrogen, so it makes them chiral. So just to give you a couple more examples here. So the big thing about a chiral molecule is that it can exist in 2 forms. It has a left-handed or right-handed form. Their mirror image cannot be superimposed. So just to give you another example, alanine. So here's the alpha carbon, it's hydrogen. Alanine has a methyl group. Okay. So here, this is going to be chiral because the alpha carbon right there has 4 different things attached to it. 4 different groups are attached to it. So again, that means it has left-handed or right-handed structure, and the mirror image cannot be superimposed. So with glycine, it could be, the mirror image is identical. But with everybody else, all the other 19 amino acids, they have the left and the right isomers. Okay, I have one more example here for you. Okay, so 2-aminopropane. And 2-aminobutane. So we're going to figure out which of these molecules is chiral. So propane would just be, we have 1 carbon, 2, 3, and then we have an amino group on 2, so NH2, and then 2 aminobutanes. We have 1, 2, 3, 4 carbons, so it's going to go on the 2, NH2. Okay, so on carbon 2 over here, we have a methyl, the amino group, and a hydrogen. So on that carbon, we do not have 4 different groups because we have 2 methyls. So that would not be chiral, it would be achiral. But on this one, so I'm just going to be looking at carbon 2, we have the amino group, we have a hydrogen, we have CH2, and on this side we have CH3. So this one would be considered chiral. So a molecule only needs one chiral carbon atom to be chiral, sort of the whole thing to be chiral. So you just have to make sure the groups around the carbon are different. So anytime you have two mirror image forms of a chiral molecule, we can call those enantiomers or optical isomers. So either one works. But they're just a kind of stereoisomer, which is an isomer that has the same molecular and structural formula but different spatial arrangements of their atoms. So it's just a kind of that. So the pairs of enantiomers have many of the same physical properties. They have the same melting point, the solubility in water, isoelectric point, and density. So again, having those two mirror image forms is just called an enantiomer. Okay, so now we're going to get into the different types of structures for proteins. So first we're going to be looking at the primary structure. Primary structure is just the amino acids connected by peptide bonds. So here we have an example of that, and the R chain or the R side chains are listed there. So this would just represent the primary structure. So it's not folded anyway, it's just the amino acids connected together in those peptide bonds. The peptide backbone has the alpha carbon, so that's what the R side chains are connected to. And then we have the amino group and the carbonyl. So all along the peptide, we call it the peptide backbone. Okay, so just to give you an idea, the alpha carbon in the primary structure has a tetrahedral arrangement. So let me give you an example of that. Okay, so here's the alpha carbon. I'm just going to write a little alpha underneath it. So we've got the amino group here, so NH. And then we would have, in the peptide backbone, it would be connected to something else, unless it was on the very end, the N terminus. And then we have the carbonyl group over here connected. And then we have the hydrogen. So this wedge means that the hydrogen is coming out at you. And then the dash shows the R group is going behind. So that's just the kind of the look, the tetrahedral look that all the alpha carbons in the peptide backbone have. Okay, so in that, with the alpha carbon, so then we would have another alpha carbon over here. It says that, the bond between the carbon and the carbonyl and the nitrogen, it's kind of like a double bond where it has no rotation around it. The double bond is kind of shared with the nitrogen, so it doesn't rotate. So we get a rigid planar unit, and it happens right here. So with the alpha carbon over to this side and the other alpha carbon. So this is the rigid planar unit. So again, there's no rotation happening between the carbon and the nitrogen because it acts like, it shares that double bond between the two atoms. Okay, so in the peptide backbone or the peptide bonds, you can have many different amino acids in the peptide. So here it says 2 amino acids can form 2 different dipeptides. So just to give you a look here. So if I had, let's put alanine and glycine together. So if I have alanine, we have that methyl group, and then carbonyl. So here's where the peptide bond happens between the carbonyl and the nitrogen of the next amino acid. So now we're going to draw glycine. So there's our alpha carbon. We have a hydrogen for our side chain and glycine, and then the carboxyl group here. So that would be an example of two amino acids in a dipeptide. But we could also draw it the other way, where we had glycine first. So it really, I forgot my positive, really depends on which side it's on. So the alanine is on the N-terminus side and the glycine is on the C-terminus side. But we could switch those and get a different dipeptide. So we do that real quick. Get rid of those R groups and redraw it now with glycine on the N-terminus and alanine on the C-terminus side. So just two amino acids can form two different dipeptides. So, you start putting more amino acids together, and then there's going to be a lot of different arrangements that you can make. So, and I think I've said this before, but each amino acid in the peptide is referred to as a residue. So we always start by naming the amino acid that's on the M-terminus, and then we end with the amino acid on the C-terminus. So this one would be glycine, alanine, and we could use the three-letter abbreviation to be able to do that. So it would be going to be so that's the three-letter code there for glycine and alanine.